Hi there, Physics 131. This is your short pre-class video introducing the reading for class 29. We're into chapter 10 now. It's called Vibrational Motion, and it opens up with this photograph of a bridge going over the Fontanka River in St. Petersburg. And this is a replacement bridge. They mentioned that the original stone bridge collapsed when a Russian cavalry squadron of 50 soldiers marched across it in step. And so there was a question here, why should soldiers avoid marching in step when they cross the bridge? And indeed, if you're marching, the idea is when you go across the bridge, everyone has to just try to walk randomly and naturally so that you don't accidentally set up a resonance frequency and collapse the whole bridge. So resonance is one of the concepts from chapter 10 we're going to kind of cover. Section 10.1 is called Observations of Vibrational Motion. So as usual, this textbook tends to start with the observations, then makes some hypotheses and does some testing experiments. So, but basically, it talks about walking. Anytime there's a periodic motion back and forth, we call this vibrational motion. And there is this little video of a cart on a spring. If you first push the cart and compress the spring and then release it, it'll stretch the spring and then pull it and then push it and pull it and push it, and you'll have a vibrational motion there. So if you analyze that, what's happening is that there is this horizontal spring force which obeys Hooke's law. So if x is negative, it pushes it in the plus x direction. If x is positive, it pulls it in the negative x direction. So there's something called equilibrium position of vibrational motion. That's right in the center. That's where the restoring force tends to want to accelerate the object. A restoring force is a force which tends to restore a vibrating object back towards its equilibrium position. So you can look at that. There's also energy in vibrational motion, kinetic energy trading off with the elastic potential energy. So when one is a maximum, the other is a minimum. You also need to know about amplitude, A. So when a cart is oscillating back and forth, you call its equilibrium position 0. Its maximum x value is plus A, and its its minimum position is negative A. So it actually travels back and forth through a whole range of 2A, right? From negative A all the way to plus A. There's period and frequency. So the time interval for one complete vibration is called the period, capital T, not to be confused with tension. And then the frequency, F, is just 1 over the period. And so the units of frequency are seconds to the minus 1. The SI unit for frequency is also called the hertz sometimes, where a second to the minus 1 is hertz. And this example, exercise 10.1, is just if you know the vibration period, you can find the frequency. So that's it for section 10.1. Section 10.2 is called Kinematics of Vibrational Motion. And before I get into that, I want to do a little digression here. So what the author is going to do is immediately start talking about the cosine function to describe the position of the mass on the spring. And for me as a student, it was always a bit of a mystery as to where the cosine came from and why it was that. So actually, if you go to Quarkus right now and look at class 29, here's this video right here, but you can click on the Google Sheet View Only. And what this does is it brings up a Google Sheet, which is owned by Jason Harlow, and it's a view only. So what you're going to see is you won't be able to make any changes to it. And if you click on view only, you could request edit access, but I'm not going to give you that. So what you need to do is actually go to File and click on Make a Copy, which would go into your own drive. So now you have a Google Sheet on your Google account that you can edit. So this is a way of kind of playing around with this mass and a spring. And I'm going to talk a bit more about this in class, but it's fun to kind of play with this. So if you have time, at time 0, a mass is at some position x, 1 meter, and it's released from rest. Its velocity is 0 meters per second. Let me actually zoom in a little bit on this. Then its acceleration, if it's a mass in a spring, is going to be, the way you would calculate it, is you'd say -1 times a spring constant, which in our case is 1 Newton per meter, that's F3, times B2, what the hell is B2? Oh yeah, that's times x, right? Because the force depends on the x, -kx, and then divided by the mass of the spring, 1 kilogram. So that gives acceleration. And then what you can do is say that on line 3 here, the time gets updated by, it's the old time above, plus F2, plus the time step. And that's kind of short, but why don't we make it, let's just do it like 0.05 seconds. Okay, so that updates that. And then the position is going to be the old position plus the delta t, which is the time step, multiplied times c2, which is the speed it used to have. So speed times delta t gives you the change in position, so that updates the position. And then the same with the velocity. The velocity is the old velocity at c2 plus the acceleration times the time step again. And then the acceleration, again, you just use this equation from Hooke's law. So what I can do now, if I want to make a plot of this, is I can select these cells, copy them, and then paste them down below. We can do maybe a bunch of steps here, and then press paste. And so what that does is it changes the position as the time goes up and changes the velocity, the acceleration goes down, I guess, and then makes a plot here of x versus time. And so this is where you start to actually see this, didn't go very far there, this what looks like a cosine curve. So notice there's no cosines in any of this. All I'm doing, let's copy some more of these, is just using this f equals -kx and copying and pasting. So just doing little teeny time steps. So it's fun to kind of play around with this. So now you're starting to see that this thing is oscillating back and forth over some time. So that kind of leads us, so this looks like a cosine curve, not quite a cosine curve. I think my time step might be a little too big, so it's not a very good numerical integration. But naturally, if you put a mass in a spring, it's going to have a cosine. It's kind of interesting because even at pi seconds for this mass and the spring constant, it's at its maximum. It takes 2 pi seconds to go right around. So now let's look at back to the textbook, and let's look at section 10.2. Section 10.2 is about the kinematics of vibrational motion. So kinematics is often position, velocity, and acceleration. So that's exactly what goes on here, is that if you look at position versus time, you get this kind of wavy curve. If you take the slope of that, you will see also a wavy curve, but it's a little out of sync with this. So for example, when you release an object from rest at its maximum amplitude A, it has 0 velocity. But then it starts shooting down towards equilibrium and it gets negative velocity. And when it passes the equilibrium position, you can see that that's when it has its maximum speed in the negative direction here. Then when it gets down to its lowest point, it stops for a moment and then starts going up again and gets to its maximum speed again when it crosses equilibrium. So every time if you notice, every time it crosses the x equals 0, that's when it has the maximum speed, either the lowest, like the negative Vmax or plus Vmax at those points. And then conversely, when it reaches its either highest point or lowest point, so its maximum or minimum value of position, that's when it momentarily stops, because that's a turning point, right, when it goes from positive velocity to a negative velocity. And then what you can do is take the slope of the v versus t graph and get the acceleration versus time graph. And then you'll see something else, which is that when it starts from rest, it has its sort of maximum acceleration. When it gets to equilibrium position, that's when it has its zero acceleration. So I think the acceleration is best thought of as the force coming from the spring. It's coming from that force, right? So when the spring is maximally stretched or compressed is when you'll have your maximum acceleration. And when it passes through equilibrium, that's when the spring is neither pushing nor pulling, and so that's when you get your zero acceleration. So that's pretty much it for that. You should go through this description. There is a mathematical description, which they talk a little bit about a circle. They go through a lot of this stuff, and then they just give you this equation 10.2. X equals a times the cosine of 2 pi over capital T times lowercase t. So it's a little complicated looking, but basically the variables here are x, that's the position, and time, that's the time. So as the time increases, you have these two constants, which is the amplitude of the vibration and the period of the vibration, a and this capital T. And so cosine, if you look at a cosine curve, it looks like that wavy thing. So this equation gives you x as a function of t. So you plug in different values of t, and you'll see it going up and down and up and down. And that's what's known as simple harmonic motion, SHM. That's the mathematical model. And it looks sort of like this, depending on where it starts from. So sometimes people put in a little constant there. I guess you could represent it with sine or cos, depending on how it starts exactly. And you can also, I guess, figure out, from this slope what the velocity and acceleration. It turns out the velocity is some constant times a sine of 2 pi over t, and the acceleration is again some constant times a times cosine. So they're all these sort of either cos or sine of the same thing, 2 pi over t times time. And all that's different are these different constants out front. So that gets you started on chapter 10, and I'll see you in class. Bye for now.